Yes, 17. 317. Okay.
So this is all the just going to take them away.
Yeah. I got the train.
You got a train back.
From Edinburgh. Yeah. Scheduled now.
Okay, cool.
I think that's one sentence that would be very nice to have the scientific. I agree with your
So we are getting the whole thing. We are no. It's like we might do that. We are
get more funding for
Yeah, that's what it's been. That's what it's been.
Well, you're close to Papacchini, right? You're the closest.
Yeah.
And I'll also make it when we get closing.
Okay, as soon as everyone is seated, we'll start the session. Welcome to the session. And our first speaker is Amir, Niknafs, Kermani. Symmetric theorem. Yes, please go.
Okay, so yeah, I'll talk about this new system called STTP. It's basically a symmetric temporal Theorem improvement. So my name is Amir, and I'm a PhD student at University of Liverpool on the supervision of Dr. Boris, Konev, and Michal. So basically what I try to start, well, I'm working with temporal logic, so I'm going to give a bit of background about temporal logic, and then explain what the system does, and some cases studies, and say, I mentioned a few of the future works that I have in mind. So, yeah, temporal logic. Basically, we are working with propositional temporal logic. Basically, propositional temporal logic is, well, it's a logic, basically, it's an extension of classical propositional logic that has operators dealing with time. And in this logic, we basically assume a linear and discrete model of time, and that has an infinite past and infinite future. So we always have a start point, and then we can go forever. Basically, that's the assumption of it. So just a bit of formalization about it. So if we have a formula in PTL, basically top and bottom are in PTL, and if any other variables, if any other propositions are in PTL, so are the as classical propositional logic, we have negations. Then phi implies psi, phi equivalent psi, and phi or psi, and phi and psi. So these are also part of propositional temporal logic. And now we have the operators that deal with time. So the first one, circle phi, basically means the next moment in time phi is true. Box phi basically means always from the point, always in the future phi is going to be true. And diamond phi is basically sometimes in future phi is going to be true. And we have phi until psi, basically means phi is true until psi becomes true. So right. So let me explain this first. So and then we have phi unless psi. Basically, it's similar to the previous one. However, psi here doesn't necessarily have to be true. So until, if you have until, psi is going to be true at some point in future, definitely. But if you have unless, then psi doesn't necessarily have to be true at some point in future. So these are basically the proposition temporal logic. However, what we try to do, we try to formalize it in a normal form. The normal form for this logic called divided separated normal form, or DSNF. We basically try to formalize the system by saying, okay, we have initial clauses. These are the clauses that are true at the very first moment in time, so at the start of the time. And we have universal clauses. The universal clauses are true all the time, so at the start and any moment in time. And also we have step clauses. Step clauses are basically clauses that are going to be true in the next moment in time. And we have also eventuality clauses that saying basically they are true at some times in future. So we have initial, universal, and step and eventuality clauses. And then what we could say, okay, the DSNF representation of a formula, we can just say, okay, this characteristic of I and U and S and E are basically our formula. Now, we can do proving on it. So one of the methods that we could use for proving such formulas are called a resolution method. There are also tableaus available, but we are working with temporal resolutions. So one of the methods is used, it's closure temporal resolution method, is being formalized by Professor Michael Fisher. And what it does, it basically operates in this DSNF form, and it applies basically a simple resolution inference rules to find contradictions. So what we're really interested in to find, say, okay, we have a system, supposedly phi, and we want to prove a property, let's say psi. So what we say basically, we want to say, okay, psi is basically phi is a model of psi. So what we could say, okay, if phi and not psi is false, therefore psi is phi is a model of psi. And then there are currently a few provers available for this that uses this closure temporal resolution method. For example, T-Spass and Temp. These are first order monodic temporal resolutions, and TRP++ is a propositional temporal logic, propositional prover for it. Now, as I said, the simple inference rules that are used for these resolutions are basically called, one of them is a step resolution. So basically, if we have R1 or P and R2 or not P, we could resolve P to get R1 or R2. And we could have it on a step resolutions. Say we have L1 implies next R1 or P, and L2 implies next R2 or not P. So we could resolve P to get L1 L1 and L2 implies next R1 or R2. And the next one is called temporal resolution, that deals with once we have eventuality in our clauses. So we say, okay, if we have eventuality, let's say eventually next L, and then we have this formula here that L implies next always not L, so we could resolve it to get always not L. And from previously in, okay, if I go back to this DSNF normal form, we won't have any of these. You won't have any of these such formulas because these are normalized. So we have to construct these sort of formulas. And the construction of these formulas are basically called loop search. So whenever I refer in my talk about loop search, that's what I'm trying to do to construct such a formulas. And it is quite hard. Let's say, okay, now. But the problems with these resolutions, with these the method is basically, these are exponential time, as most of the provers are. But it's really difficult. It's really difficult to prove a proper specification as the problem grows larger. And also, based on my experiments, and well, not my experiment, based on the experiments, basically the loop search part of this resolution is quite hard and it's quite slow, at the slowest I've found it. So what I try to do, I try to reduce the complexity of temporal resolution, basically finding the loops and do resolvents on the loop search on a specific system. So I try to reduce my problem. I try to say, okay, I'm just looking at the certain systems that are, I call them symmetric systems, and try to find loop search. I try to find the loop using these systems. So what are these systems? It's basically quite simple. The system that consists of identical tasks which can be same for all the involved processes. One of the examples for this system could be parameterized systems. So parameterized systems are basically distributed system comprising of n identical processes, and each of the processes have several inner states. So for example, process A has 3 states A, B, C. Also process 2 is going to have A, B, C as well. And these processes can interact with each other using the states that they have. For example, we say, okay, if process 1 is in a state A, then we're not going to have process 2 to be in a state B, for example. Yeah. So what does this prover does, STTP? It's a symmetric temporal Turing prover. How it works is basically using temp and TH paths as black boxes. So we just ignore how they do stuff, how they do these resolvents. And the input for this, so I try to restrict the input, of course. So what I try to do is say, okay, supposedly we have this temporal specification psi j, and j is supposed to be the number of processes we got. And we have at most one eventuality clause, diamond L. And why I say at most one eventuality clause, and the reason is because we can transform a multiple number of eventualities into a single eventuality. Well, I'll show the references later on, so you can see it. So it is possible to do that. And also J, basically, suppose we have a system and we want to prove some properties, we need to have at least a minimum number of processes to prove a certain properties. So if there are processes interact with each other, so if 2 processes interact with each other at most, therefore we need 2 processes to prove some properties, or well, 2 or more processes to prove some properties. So how does the system work is basically what we do. We basically run a prover on one of these systems on 5J, and try to analyze the resolutions. So we try to find out what we get from the system on side J, and then heuristically guess a certain properties, a certain formulas for the next number of processes. So if we add extra process to our specification, we can heuristically find the temporal resolution. So we basically avoid doing all these steps all over again. And then once we find, since it's heuristic, therefore we have to check. We have to check that these are true. These are indeed eventualities for phi j plus 1. And once on the successful check, we can basically say, okay, we know the check is true, therefore we can get rid of eventuality and replace it by well, let's say we have this guess psi, and we can say, okay, we get rid of eventuality and replace it with psi. So psi is supposed to be the temporal resolvent for the eventuality. Of course, for the bigger system with ij plus 1 processes. So basically, how these heuristic guess work is quite simple. What we say, okay, if we add extra process to our already defined specification, if we add a process to already define a specification, it's not going to affect the loop it's going to affect the loop as much as any other processes. For example, so suppose we have two processes, we do that, and then we have, each of the processes have two states, A and B. And for the loop resolvents, we only need state A of each process. Therefore, we say for the next generation of a system, we're only going to use A state, and we're going to ignore the fact that B exists. So the heuristic is based on the previously found states. Right. So that was basically the heuristic. And how can we check these sort of properties? How can we check if it's indeed a loop? So a loop has basically two properties. So if you have a system and the loop is going in our system, the loop is going to say if you have an eventuality L, we say okay, the loop is going to say the next moment not L is true, and also the same. Okay, if we have a combination of universal clause and step clauses, we say the loop preserves itself. So always the formula implies itself. So to check this, we are going to generate a new specification that basically the initial clauses are going to be the loop that we found, and step clauses are what we had previously in our specification plus the new step clause, and also the universal stays the same, and we get rid of eventuality. And we try to check that by just running the Theorem prover. So nothing. So basically, as I said, we use the Theorem prover as black boxes. We just run the Theorem prover, and we can check the contradictions. If we find the contradictions for the I mean, there were two checks need to be done. So if both of the checks we observe contradiction from both of the checks, therefore this formula is our loop. And yeah. So I try to find a good example, which is quite useful in the protocol. So MSI is a cache coherence protocol that is that try to find that is quite useful. That has certain properties in memory management in cloud computing. So I try to prove it with temp. So this is the time that I get from the temp. And P is basically, it shows the number of processes that we have within our specification. So by having running on temp, we basically can prove up to 5 processes. However, by running it on STTP, we try to get it to 8 processes. It is quite slow, as you can see. It's about 2 hours had to run it to prove it. And these are the number of clauses that are generated. So on the temp, I mean, on the 2 processes, we have about 3,500 generated clauses, but STTP is like 500, around 500. And as you can see, I mean, as the problem grows, the number of generated clauses just dramatically increases. It is the same with STTP. However, the rate of growth is a lot smaller compared to temp. Therefore, we can prove a more, but larger system for our but basically we can prove a larger system of for MSI with for MSI protocols. Yeah, and that's basically it. And for the future work, as I said, STTP is it's an early stage of development, so a lot of things have done the programming is really done badly since I did it myself, but it can improve a lot more since it does things over and over again, because of using the provers as black boxes. So that's one thing I need to work on. And also, he only uses, at the moment, he only uses two of the provers, but there could be more provers that are already out there. So we can basically use it as a benchmark. So just a benchmark for symmetric system. And the next thing that I'm working at the moment is basically, we can say guess a loop, but how about if we guess the resolvents or the step resolvents that are done during the process. So if we can do that, we can considerably reducing the number of generator resolvents in our proof. And that's it. And the references that I've made, if anyone interested. So, and that's it. Yeah, great. Thanks for listening.
Any questions? Please, Mom.
I haven't quite understood the relevance of this. You said symmetric. So what is symmetric about? What is the relevance of that?
Okay, so basically what symmetric means is symmetric basically try to find similarities within a smaller problem in order to generate in order to find some useful information that can be used for a larger problem of same specification. What I mean by larger problem is basically having more processes involved in our specification. And yeah.
Any other questions? Yeah, please.
What property were you proving for this MSI product?
Okay.
Safety, liveness, or what?
Right. The property I was proving is called equality. So basically, two processes at the same time cannot be in a specific state. So MSI has three specific states. One is initial. One is I, M, and S. So two processes at the same time. One cannot be in S at the same time. The other cannot be in M.
So some kind of mutual exclusion?
A mutual exclusion, yes.
So it's like safety property?
Yes, that's a better way of saying it. Yes, right. It was a safety property.
No, I'm just a bit. I don't know if that's the best example though, because like there are better ways of proving safety and liveness for cache clearance protocols. There are other techniques out there.
Yes, there are better techniques out there. At the moment.
One of them is actually like in the paper that you cited there. So the second one. So I think they managed to have an automatic technique for showing it for all n, as opposed to just like 1, 2, 3, 4 up to 9 or something like that.
Well, that's exactly. So what they try to do, they try to do it for infinite number of states, and infinite number of processes, and it's exactly, you're right. There are better ways. However, what I tried to do was basically introduce symmetric into temporal resolutions, and what I mean by symmetry, to find similarities from the previous state, previous generation, in order to guess and in order to make use of it for the next set of systems.
So do you think you can sort of combine it with some kind of techniques like, I don't know, network invariance or something in order to generalize the whole,
But I mean, yes, this thing eventually should be generalized. That to say, okay, if you know it for like 9 processes, then we should be able to do it for like 100 processes. Yeah.
Okay, thank you. Our next speaker is Fabio Papacchini, Temporal and Modal.
So, hi everybody, I'm Fabio Papacchini and I'm here to talk about new minimal integration for model logic. So, first of all, let's have a bit of background. So, why we want to generate models, why we want to generate minimal models. And the reason is that in computer science, model generation and minimal model generation are useful for tasks like hardware and software verification or for diagnosis purposes, for common sense reasoning and so on. And since a lot of logics are used in computer science, this model generation, minimal model generation have been studied for classical and non-classical logic, so for temporal logic, first-order logic, and so on. Now, when talking of minimal models, the first question that we have to answer is what minimality criterion we are using. And in literature, we can find several minimality criteria, like domain minimality, where we try to build models with the smallest domain. And the problem here is that smallest domain doesn't mean that you have a meaningful model from a scientific point of view. We can have the minimization of the interpretation function for a set of predicates or for all predicates. In the latter case, we call this kind of minimization minima Hermann models. And the problem here is that minima Hermann models are strictly based on syntax, on the syntax. What we want to do now is to present a minimality criterion that somehow is an evolution of the minima Hermann models. So we want to minimize the predicates, but at the same time we want to take care of the semantic of the model. And we also want this minimality criterion to be generic enough to be applied for a variety of modal logics. Another point of my talk will be to give an idea of a possible tableau calculus for the generation of these minimal models. Now, the minimality criterion, as you could have seen in the title, involves subset simulation. So first of all, let's have a look what subset simulation is. And subset simulation is a relation between the nodes of two graphs, so the nodes of two models in modal logic. And this relation has to fulfill some properties. So first of all, the property that, where is the pointer here? The property that the label of a node should be a subset of the label of the other node. So in this case, we have this black node that can be related with the red node and the green node because Q is a subset of Q and T and Q and S, but cannot be related with the yellow node because Q is clearly not a subset of S. Then the other point is that if this node has a successor, then the nodes that are in relationship with this node must also have a successor, and this is the case for both the red node, because it has at least two successors, and the green node that has one successor. And then there is a kind of recursive call of this subset simulation. So also the successor of Q of this black node must be in subset simulation with some other node. So in this case, we have that this red node that was our first case at the beginning is no longer a valid subset similar, is not subset similar with the black node because it doesn't have any successor that is subset similar with P. But the green node is. Some other definition of subset simulation is we can talk of full subset simulation if we have this, if this relationship, subset simulator relationship holds for all the nodes in the domain of the subset simulation. And we can also talk of maximal subset simulation if there is no subset simulation that is greater than the current one. And I'm saying this just because we are interested only in full and maximal subset simulation. They are somehow easier to compute. There is already an algorithm for computing them. Now, subset simulation on its own is not a minimality criterion, but it has some property that can be used to make it, to use subset simulation as a minimality criterion. And specifically, subset simulation is reflexive and transitive, and therefore subset simulation is a preorder. And we can exploit this preorder and say that the minimal models are just the minimal elements of the preorder. So the example that is here, we have these 5 models, and the minimal models are the models on the left, following the preorder. But we can already see some limitation of subset simulation in this case, because this model is clearly completely embedding this other model. So for this reason, we want also to improve the minimality criterion by imposing a test on the symmetric models. We talk of symmetric models because this one subset simulate this and this one subset simulate the upper one. So the test that we can do on the symmetric model is the use of simulation. Simulation is basically like subset simulation, but instead of using subset relationship, we use a equality relationship. And this allows us to reduce the number of minimal models and also to recognize bisimilar models. So the example that is here is actually the same minimal models that were in the previous slide, and we can see that these two are symmetric under subset simulation. But if we use the notion of simulation, we can see that this one simulates this other model and not the other way around. So we can consider only the model on the right, the minimal one. Okay, now that the minimality criterion is presented. Wait, there was a slide in the middle. So what are the properties of the minimal model that are generated with subset simulation? First of all, subset simulation is nice because it's applied directly to the graph representation of the model. So this is a way of taking into account the semantic of the model. And nice property is that if you unravel the model of a model, you can have a finite unraveling of the model, or you have an infinite unraveling of the model. And subset simulation will prefer finite unravel models rather than infinite unravel model. This means that the minimal models probably won't be domain minimal models. We will try to avoid loops as much as possible. As I said at the beginning, we were trying to minimize predicates. So in this case, we are able to minimize the content of words. So we will try to have a model with the least number of propositional variable true in it. And since it's working directly on the graph representation of the model, so it's exploiting the Kripke semantic, and many model logics are based on Kripke semantic, and therefore this minimality criterion is suitable for many model logics. Now, how can we compute these minimal models? So here I'm going to give some idea for a tableau calculus. The input of the calculus is a model formula in negation normal form. This is mainly because in this way we can avoid some rule. And one rule that we can use is selection-based resolution. Basically, it's already used in other calculus for the minimization of models. And the idea is that we need a closure rule. And this rule will actually be our closure rule, because if we have Pn and not Pn, we will be able to derive a clash. And the other point is, since the minimality criterion is based on the positive information on words, if you have a disjunction with negative information, then we don't have to expand it if it's not really necessary. Another rule involves basic classification. The idea is that classification actually helps in generating minimal models. On the other hand, we don't want to compute the closed normal form from the beginning. So we can do it in an incremental way during the calculus, using this idea that, okay, if there is some part of the clause that is negative, we don't have to keep expanding it. So a combination of these two rules can actually result in a reduction of inferences needed. Then we need some rule for some branching rule in case of disjunction that contains only positive information of information we can't decide if they are positive or negative. But we also want to close branches that are generating non-minimal models. And we can try to do that by using a complement splitting rule. So to insert some negative information here. Complement splitting rule is already used, so the idea is just we have some positive information, so P1 or Pn appears in this phi plus. We try to negate them on the left branch. And as a result, if this clause is already satisfied by one of these P1 to Pn, then we don't, this rule is not actually needed. We don't have to go to the left branch. We can directly go to the right branch and try to find out why the disjunction is already satisfied. We need a rule for the diamond formula, and this rule is probably one of the most expensive rules of the calculus. So the idea is that we need to check almost all the models of the formula, and therefore we can't just create a new successor and check if the formula can be satisfied in the new successor. We need to try all the already existent entities in the domain, so all the existing words, and in the worst case to create a new successor. This is basically necessary for the completeness of the calculus. The box rule, okay, the box rule is the standard rule that you can find in basically all tableau calculus for modal logic. Now, what are the properties of this calculus? So far the calculus is refutational sound incomplete. So if the formula is satisfiable, we will find a model. If the formula is unsatisfiable, the tableau will be a closed tableau. And is minimal model complete, which means we will generate all the minimal models. The problem for this calculus is that the calculus is not minimal model sum. So while generating models, we will generate a lot of non-minimal models. And we have to find a solution for this. We have to find a way of making this calculus sound. And the idea is to close the branches where you can install a model that is not minimal. So this is done incrementally. So we generate the models in an incremental way, and incrementally using this expansion strategy. So we always select the leftmost branch with the least number of words, which means we generate all the domain minimal models first, and then we keep increasing the domain size. While doing this, we try to close branches as much as we can. So how we can close branches? We can close some branch actually before the branch is complete. So it's possible that the partial model is already not minimal. So we have some model that is already been extracted. We are building a new one, and we realize that the new one we are building is already not minimal, and any possible extension of this non-minimal model will result in a non-minimal model. In this case, we can immediately close the branch from which this partial model was extracted. In other cases, we won't be able to recognize that a model is not minimal, and we need to completely expand the branch. But once we have the fully expanded branch, we can extract the model. This one won't be a partial model, but will be a proper model, and we have to compare it with the currently minimal models. This comparison will tell us if the model is minimal up to now, or if one of the previous models was considered minimal is not really minimal, but is somehow subsumed by the new one. And we have to close the branches accordingly, which means we would have to close previous branches or the current branch. Or maybe none of them, because the new model is actually minimal. So, to conclude, the minimality criterion just presented, I think is following the semantic of the model formula better than other minimality criteria like domain minimal models. And is suitable for model logic, for many model logics, because it's based on the cryptic semantic. The calculus can be easily generalized to cover more expressive logic like multimodal logic and the extension with well-known axioms, universal modalities, and so on. One problem of the calculus is termination. So to have all the minimal models, we have to actually completely generate all the models and somehow test them. Termination of the calculus depends on the logic we are working with. So if it's multimodal logic K or Ks, then with reflexivity and symmetry, we will terminate. That's not a problem. But if we are using, for example, if we have logic like S4, we know that transitivity will lead to infinite models. We won't be able to say which model is actually the minimal one, at least not in a finite amount of time. So what we want to do in future is to implement the calculus, if possible, at least some variant of it. So the idea is that we can study some restriction that we will lose completeness, we will lose minimal model completeness, but we will have a more practical calculus. And we also want to study the possibility of extending this minimality criterion to fragment of Foster logic that have some kind of bisimulation property like the guarded fragment or the guarded negation fragment. And that's it. Thank you.
Thank you. Fabio, questions for Fabio? I wanted to ask what motivated your choice of a tableau calculus versus resolution, because it looks to me like you can have a nice translation and perhaps use good tools to have your minimal model generated by resolution rule.
Well, okay, I am actually using a kind of resolution rule because the selective-based resolution is actually taken from resolution. That's true.
Yes.
Personally, I prefer tableau calculus. I found them more goal-oriented somehow. So I'm just breaking down the formula. I'm not inferring new knowledge from merging clauses. The other point is I don't want to generate clauses if it's not necessary. And most of the resolution calculus is based on the causal normal format. I know that there are resolution calculus and they are not based on clauses. But yeah, I would say that the main point is the subformula property is easier to handle with tableau rather than resolution.
Any more questions? Please.
I have sort of an intuition why you're interested in these minimality, but do you have examples where it is useful? So I was thinking of what I was talking about previously, to sort of find minimal sets in whatever bar models to describe that certain things don't work properly yourself. But why are you interested in minimality? Can you make it more specific perhaps for me?
So depending on the application, so the idea is to be able of studying a counterexample when you think a formula is valid and then you find out a counterexample. You want to understand why you have this counterexample. Clearly, the study of minimal model can help you in understanding, having a better understanding. On the other hand, if you're referring directly to this minimality criterion, because the usefulness of minimal Herbrand models is, you can find explanation why a Herbrand model can be useful. So the minimal Herbrand model can be useful in several papers. And the reason why I'm using this new minimality criterion is because I didn't like Herbrand models in general. I didn't like this idea of being somehow bound to the syntax of the formula. I want to be a bit more expressive. I've seen Herbrand model looking at them and say, okay, but this one is more or less the same as the other one. What is just modulo the notation that is used. That's why I try to overcome this limitation using subject simulation. On the other hand, it's easier to generate Herbrand model than to generate this kind of model. So practical application at the moment, as it's formulated now, I can't see a practical application because it's just too complex to generate these minimal models. But I think we can somehow tune it to be somewhere in between Herbrand models and the original theoretical idea of subject simulation to have useful minimal models that are understandable.
Do you go from infinite to finite then as well? Or?
Yeah, so I'm working with modal logics, and many modal logics have the finite model property. So if I can find something in between, something that is, okay, a finite model that can give me information from a semantical perspective, I would be happy to reach that point. Maybe it won't be, strictly speaking, minimal, but will be easier to understand it, to give information to who's watching the model.
I think a challenge for you would be to find unique minimal models, or unique minimal Herbrand models. As you mentioned in your talk, sometimes you find minimal models which are very similar, and both are minimal, but one is very similar to the other.
Yeah.
So I think that that hasn't been done, finding one unique minimal Herbrand model.
I think it's possible in few arguments of possible logic. So I know that there are studies where you actually have one minimal Herbrand model. So in that case, it's a quite restricted fragment.
Okay, and you, sir, had a question, the final question? Or?
Yes, just a quick
yes,
question. So
please,
this notion of subset simulation, is it the same as the standard notion of simulation in between Turkish structures? Or?
Well, depends. So in model checking, you find the notion of simulation, which is the same as this one. The difference is that I'm using the subset simulation relationship rather than equality. So simulation is, depending what paper I'm referring to, you will find with equality. But I can tell you that in there are a couple of description logic papers where they talk of simulation meaning subset simulation. Yeah. So, if, I mean, people.
So what about in this the third paper that is cited by Monica Hensinger?
No, the one cited by Hensinger is they're using simulation in the meaning of equality. So this was that the subsets in the relationship holds. In that case, it's the equality relationship holds between the
So is it just a technical difference or like a major difference in terms of the results and algorithms and things that you can prove?
So simulation is every time you have a simulation, you have a subset simulation, but it's not true the other way around. Right. So you can have subset simulation, but you don't have simulation relationship.
I know, but what I'm trying to say is like is it just when you look at this notion now, do you all the results that that you can prove in the for the standard for the other notion of simulation, is that like does it easily adapt to this notion or not?
Not all the results. Some of them are, some are not. For example, if you have two models and one simulates the other one and also vice versa, then you can say that they are bisimilar. But bisimilarity doesn't hold for subset simulation, so you can have symmetric models that are not bisimilar. But for example, the algorithm that is presented in Hensinger paper can be adapted for subset simulation. It's not so difficult.
Okay, thank you. Our last speaker is Michal Zawidzki.
Yeah.
Thank you very much. My talk will concern a hybrid tableau algorithm for a modal logic with global counting operators. And by hybrid, I mean an algorithm involving two types of reasoning, namely logical reasoning, or logical part of reasoning, and arithmetical part of reasoning. Does it work?
Yeah, it doesn't.
Sorry, it's a wrong mode.
Yeah, but the phone is not working.
Okay, so let's start with a brief overview of modal logic and enumeration of aims. Well, there are already some algorithms dealing with modal logic with global counting operators present, but what they've got in common is that they treat the arithmetical reasoning and logical reasoning in the same way, whereas the global cardinality constraints involved in the logic will indicate that we could use some more advanced tools to deal with arithmetical part of the reasoning. So, and the logic itself is very interesting due to its expressive power, which significantly exceeds the expressive power of ordinary modal logic. Many things can be expressed. Nominal is the cardinality of a domain, or some non-standard frame conditions. So what I want to do is to devise an algorithm that deals with cardinality constraints separately. And as it turns out, the arithmetical part of the algorithm also serves as a blocking mechanism, because even though the logic enjoys the finite mode property, it can lead to infinite derivations in ordinary tableau calculi when no blocking is involved. So as it turns out, we can dispense with explicit blocking tools and only use the arithmetical toolkits. All right, so a brief overview of modal logic. I think most of you are familiar with the notion of modal logic, but just for the record. Modal logics are extensions of propositional logic. We augment the propositional logic with modal operators, box and diamonds, and initially they express possibility and necessity, but well, a long time ago we abandoned this narrow perspective. A model, the so-called Kripke model for a modal logic, is a triple consisting of a domain, an accessibility relation, which is, in the case of modal logic K, an arbitrary binary relation over a domain, and evaluation function that assigns to each propositional variable from the signature a subset of a domain, a subset of nodes that satisfy this propositional variable. So we can identify a model with a directed graph with sets of formulas at the nodes of this graph. So a diamond formula holds at the nodes whenever there is a node accessible from the nodes where the formula under the scope of diamond holds. And a box is a dual operator to diamonds, and a box formula holds whenever in every R successor of R nodes the formula under the scope of box holds. And the novelty modal logic with global counting operators are global counting operators themselves, and they allow us to express the cardinality of the set of nodes that satisfy a particular formula. So they are of the form displayed. Yes, and the example shows a situation where exactly two worlds satisfy P. Alright, so that's for the, sorry for the typos not occurring from time to time throughout the presentation. So our algorithm deals with the well-known satisfiability problem. So given a formula, we ask whether there exists a model satisfying this formula. And we are searching for such a model. So if we want to prove that a formula is valid, this procedure is a refutational procedure. So we need to check whether there exists a model for a negated formula under consideration. Okay, so we explore the notion of a tableau. I just put the conditions for the record. The tableau is, well, broadly speaking, a form of a model. So tableau satisfies all the conditions for Boolean formulas and modal formulas as well. The conditions are quite straightforward, and as you can see, the notation reflects more or less the notation of Kripke models. So we've got these conditions written here, and the conditions deal with all kinds of formulas. So that's the standard notion of a tableau. Yes, in the constructive approach to tableau calculi. Tableau, for instance, in the talk of Fabio, tableau means something different, a derivation tree, but we treat the tableau as an abstracted form of a model. So what we basically do during our derivation is constructing a model, an explicit form of a model, a completion graph. So a completion graph is not yet a model itself, but the existence of a completion graph is proven to be equivalent with the existence of a model. So, right. So we start our derivation with a formula, obviously, with a formula under consideration, and with a graph where we've got only one node, the empty accessibility relation, and as you can see, we replace the letter V standing for valuation with L. That abbreviates probably labeling function. And the labeling function labels our unique node with the formula under consideration. So that's the starting point of an algorithm. And as you will see, we also add some additional elements to our reasoning, referring to the arithmetical parts. Okay, so these are two examples of logical rules for conjunction and disjunction. These are quite obvious and straightforward, so we just decompose the complex formulas. Whenever a conjunction holds at a node, we also add to the label of this node two conjuncts. And the disjunction rule is a non-deterministic rule. We add one of the conjuncts chosen non-deterministically. And usually if we have a look at the constructive tableau calculi for logics with counting, unfortunately constructive tableau calculi don't deal with logics with global counting, because global counting is attached to a universal or total accessibility relation, which is not simple. When you reason about non-simple accessibility relations and counting operators added to these relations, unfortunately such a procedure turns out undecidable. Anyway, so these rules, what they basically do, whenever you've got the cardinality constraint of the form, there are more than n worlds satisfying a particular formula, they just check through a domain of a model and see if there are already n+1 worlds that satisfy the formula under the scope of counting operator. If that's the case, they just they are not executed. If it's not the case, they introduce n+1 worlds. Right, the less than rule is slightly more complicated. If, for instance, we impose the condition that there should be less than n worlds satisfying a formula, a certain formula, for instance phi, and there are already n or more worlds satisfying the formula phi, we need to shrink some of the worlds. We need to remove some of the worlds of our model. Usually we just identify pairwise. We identify pairwise the worlds that can be identified if it does not lead to a clash. So, but we proceed in a slightly different way. First of all, we treat all the modalities as graded modalities, as local counting modalities. So we turn diamond formulas into counting diamond formulas, and the global counting into local counting formulas. What we basically do is we attach to each occurrence of arbitrary kinds of modality, we attach a new accessibility relation. And what we claim is that when we expand a formula, the accessibility relation attached to a formula is exhausted. So there are no more successors, but these introduced to a graph by the application of a rule for counting local modalities. So, and we need to switch the conditions for our tableau according to what was said. We replace the conditions that were concerning diamond and counting modalities with these conditions, slightly more elaborate. Right, so we also make use of the atomic decomposition strategy. It's conceptually simple idea. Well, if we've got more than one accessibility relation over the domain of our model, the fillers, so the successors with respect to these accessibility relations, can, or the sets of fillers can overlap. This image well presents the situation for 3 accessibility relations, but in principle we can do it for arbitrary accessibility relations. So we partition our model into the disjoint partitions of fillers with respect to certain accessibility relations. They are disjoint, these partitions, and we map each partition to a partition symbol using the function alpha. So yes, that's an informal explanation of what atomic decomposition does. And the formal explanation is it divides a domain of a model into disjoint partitions that are defined in the way displayed here. Right, we also modify our choose rule. So as I said, we need to introduce another element to our graph, namely the EQ set, which is a set of equations and inequalities of the form displayed here. So the equations and inequalities basically say the cardinality of a partition is greater than or equal to, and so forth. And we non-deterministically choose whether a partition should be empty or not, if it hasn't been done before. So we obtain a set of equations and inequalities, and the inequality solver attached to our algorithm should return us a solution. So a solution is performed by the fill rule, which is a bit complicated, but I can obviously explain it to you in details if you want to on another person session. And when we are done with this, we carry on with the derivation. So, right, what are the remarks that have to be done? Such an algorithm has already been devised for a logic that has the tree model property, and the situation is easier because we don't need to keep track of all the inequalities throughout the whole derivation. We can focus on a particular node, and when the node is expanded, or the formula of the nodes are expanded, we are done with this node, and we don't need to take care of the node anymore. The situation here is different because the cardinality constraints are global. So, what are the advantages of the approach? Well, minimality of a model obtained, but by minimality I mean domain minimality of a model obtained with this procedure, and in some specific conditions the performance is better than the performance of standard tableau algorithms for this logic. What are drawbacks? Well, unfortunately, large non-determinism factor. First of all, the number of possible minimal solutions is doubly exponential in the number of roles, so accessibility relations occurring in the EQ sets. And second of all, the field rule is no longer deterministic as in the previous calculus. So the future work concerns investigating whether this non-determinism factor can be lowered in some way. All right, thank you very much.
Any questions for Michal? So how will you decrease the non-determinism factor?
Well, I'll probably present it as something that has been done if I know it, but I've just started to investigate the topic, so I don't know yet. Perhaps some of the minimal solutions returned by the inequality solver can be excluded in an algorithmic manner, but I don't know yet, unfortunately.
Do you have any correctness proof for your algorithm because it has a sequence of very involved rules?
Yes, I mean by correctness you mean soundness, completeness?
That's right.
Yes. I've got a proof of soundness. They are both soundness and completeness. They are quite easy to conduct, I would say, even though it looks a bit complicated. But they are based on the already existing proofs for the logic ALCQ probably.
So what is the most expressive logic that you can handle?
With this algorithm?
Yes.
Well, this algorithm was devised specifically for this logic, which is already very expressive. Its expressivity covers the expressivity of hybrid logics without binders, for instance.
Okay, if there are one last question.
So how does this relate to first order logic? I mean, usually like model logic you can embed in first order logic with two variables, something like that. So how does this extension do that?
Well, you can obviously set a standard translation function into the two variable fragment of first order logic with counting quantifiers. But obviously there are differences in complexity between this logic with cardinality constraints coded in unary and coded in binary. The first one is x prime complete, and the second one is next prime complete. So, but yeah, the translation is standard. You can also translate it into first order logic with two variables, ordinary first order logic with two variables when you nest there's a sequence of quantifiers. So if you've got equality, then it's two orders.
So it doesn't help in terms of complexity if you translate to first order logic or something like that.
No, it can't help. I mean, in the case of binary coding, the complexity is preserved because two variable fragments of first order logic with counting quantifiers with yes, it's next prime complete. But also under unary coding assumption, it is next prime complete, whereas this logic is x prime complete, so it's significantly less complex.
Okay, thank you very much. This concludes our session.
Perhaps slightly less time for lunch, but I suggest we still stick to the timetable. I mean, we join here at 1:30.
Right, yeah.
Thank you.
Oh, okay.
Not today. When you see, I'm just sitting here.
Only my job.
I
do it one after another.